What is analytical chemistry? Welcome. This first video sets the foundation for everything that follows in this course. Before we touch a single instrument or run a single sample, we need to understand what analytical chemistry actually is, why it exists, and why it matters. Let's start with a few questions. How does a doctor know your blood sugar is too high? How do environmental agencies know whether a river is safe to swim in? How do customs officials detect a banned substance in a shipment? How does a pharmaceutical company confirm that every tablet coming off a production line contains exactly the right dose? The answer in every case is analytical chemistry. And once you understand that, you start seeing it everywhere. So what is analytical chemistry? At its core, analytical chemistry is the science of measurement. It's the branch of chemistry concerned with identifying what's in a sample and determining how much of it is there. Everything in this course flows from those two questions. What is present? And how much? The first question, what is present, is called qualitative analysis. The second, how much, is quantitative analysis. You'll hear those terms constantly, so let's make them concrete. If you take a water sample from a lake and ask, is there mercury in this water? That's a qualitative question. If you ask, how many parts per billion of mercury are in this water? That's quantitative. In practice, most real analytical work involves both. You identify the substance and you measure it. Now here's a useful way to think about analytical chemistry relative to other branches of chemistry. Organic chemistry makes molecules. Physical chemistry studies the behavior of matter and energy. Biochemistry investigates the chemistry of living systems. Analytical chemistry measures all of it. It's the backbone that supports every other branch. You simply cannot do modern science without it. There are different ways to categorize analytical methods, and it helps to know the landscape before we go deep on any single technique. One way to divide methods is by what you're measuring. Chemical analysis identifies elements, ions, or molecules, for example, detecting lead in old paint, or identifying a drug compound in a blood sample. Physical analysis measures properties like particle size, viscosity, or melting point. Biochemical analysis targets biological molecules, proteins, DNA, hormones, metabolites. Another way to divide methods is by scale. Macroanalysis works with gram-scale samples. Trace analysis works at parts per million or parts per billion, amounts so small they're almost unimaginable. To put that in perspective, 1 part per billion is roughly equivalent to 1 drop of water in an Olympic-sized swimming pool. Modern analytical instruments can reliably detect concentrations far below even that. The most important division for this course is between classical methods and instrumental methods. Classical methods, sometimes called wet chemistry, include things like titrations, gravimetric analysis, and precipitation reactions. These are precise and well understood, and they've been used for over a century. Instrumental methods use physical or physiochemical properties to analyze samples, things like chromatography, spectroscopy, and electrochemistry. Instrumental methods are generally faster, more sensitive, and capable of handling complex mixtures. They are the dominant tools of the modern analytical lab, and they are the focus of this course. Before we look at applications, let's walk through how analytical work actually gets done. There's a process, a workflow, and understanding it will help you think more clearly about every technique we cover. The first step is defining the problem. What do you actually need to know, and why? This sounds obvious, But a poorly defined analytical question leads to wasted time and bad data. You need to know what you're looking for, what level of precision you need, and what decisions are going to be made based on your results. The second step is sampling. This means obtaining a representative portion of the material you're analyzing. If you're testing a tanker truck full of chemical solvent, you can't analyze the whole truck, you take a sample. But if that sample isn't representative of the whole, your results are meaningless. Sampling errors are one of the most common and underappreciated sources of error in analytical work. The third step is sample preparation. Raw samples are rarely ready to go straight into an instrument. You might need to dissolve a solid, extract a compound from a complex matrix, filter out particulates, or concentrate a dilute solution. The techniques we cover in the first half of this course, including adsorption and solid phase extraction, are fundamentally sample preparation tools. The fourth step is measurement. This is where the instrument comes in. You apply your chosen analytical technique and collect data. The fifth step is data analysis. Raw instrument output, a chromatogram, a spectrum, a signal, has to be interpreted. That means applying calibration, performing calculations, and applying statistics to understand how confident you can be in your results. And the final step is reporting. Your findings have to be communicated clearly and honestly to whoever is going to act on them: a clinician, a regulator, an engineer, a judge. This workflow repeats itself throughout this course. The techniques change. The workflow doesn't. Now let's talk about where analytical chemistry shows up in the real world, because the answer is almost everywhere. In medicine and clinical diagnostics, analytical chemistry is what makes blood tests possible. When you get a panel done at a doctor's office, instruments are measuring dozens of compounds simultaneously: glucose, cholesterol, enzymes, electrolytes, hormones. Drug testing in clinical and workplace settings relies on chromatographic techniques nearly identical to what you'll learn in this course. In environmental science, analytical chemistry is how we monitor air quality, test drinking water, measure pesticide runoff into rivers, and track heavy metal contamination in soil. Environmental regulations only mean something if we have the tools to enforce them, and those tools are analytical. In the food and beverage industry, analytical chemistry verifies that nutritional labels are accurate, detects adulteration, for example, olive oil cut with cheaper oils, and ensures that fermentation processes are producing what they're supposed to produce. In pharmaceutical manufacturing, every batch of drug product has to be tested to confirm it contains the right active ingredient at the right concentration, with no harmful impurities. The margin for error is extremely small, and the analytical methods used are tightly regulated. In forensic science, analytical chemistry is used to identify substances at crime scenes, match trace evidence like fibers or paint, and confirm the presence of accelerants in arson investigations. And in sports, anti-doping agencies use highly sensitive analytical techniques to detect performance-enhancing substances in athlete samples, sometimes at concentrations in the parts per trillion range. The common thread across all of these is this: a decision needs to be made, and that decision depends on knowing what's in a sample and how much. Analytical chemistry is what makes that knowledge possible. So where does this course fit into all of that? We're going to focus on two major technique families. The first is adsorption-based methods, understanding how certain materials selectively bind compounds, and how we exploit that to separate and concentrate analytes from complex samples. The second is gas chromatography, one of the most widely used analytical techniques in the world, capable of separating, identifying, and quantifying volatile compounds with extraordinary sensitivity and precision. Both of these techniques are workhorses. They're used every day in environmental labs, pharmaceutical companies, food testing facilities, and forensic labs around the world. By the end of this course, you won't just know how they work, you'll understand when to use them, how to trust the data they produce, and how to troubleshoot when something goes wrong. To summarize what we've covered, analytical chemistry is the science of measurement, built around two fundamental questions: what is present, and how much. It encompasses qualitative and quantitative analysis, spans classical and instrumental methods, and follows a systematic process from sampling through to reporting. And it underpins nearly every field of science and industry you can name. In the next video, we'll talk about sample preparation, why it matters, what can go wrong, and how it sets up everything that comes after.